Alright, so this video is going to go through very briefly all of the equations from third and fourth quarter. I have them sectioned off kind of by unit, and I'm going to go through it. Keep in mind, this isn't a detailed, like, how do these things work and stuff. For that, you need to go into their individual videos. But starting right here with this square right here, which for some reason my mouse isn't showing up, but the one right above me, that's for thermal energy. So in this case, Q is heat energy, M is mass, lowercase m is mass, capital C is specific heat, change in temp is delta T is change in temp. The Q is the same, the M is the same. The L, capital L, is also, that's going to be latent heat. And for those, typically you had a sheet of paper with all those listed on it. Considering I doubt any of you took it home, maybe some of you did. I will give you those in the problem. If there's a semester final question dealing with it, I'll give it to you. This is change in length is equal to this constant for the different substance times the initial length times the change in temp. This is change in entropy is equal to heat divided by temp. This is efficiency is work over the heat transfer to the hot reservoir, or 1 minus heat transfer to the cold reservoir divided by heat transfer to the hot reservoir. Maximum efficiency is equal to 1 minus the temperature of the cold reservoir divided by the temperature of the hot reservoir. Okay. Keep in mind, honors and regular maybe didn't use some of the same equations. Okay. And then maximum work that an engine can do is equal to 1 minus TC is cold temperature, the temperature of the cold reservoir. TH is temperature of the hot reservoir. QH still is heat transferred to the hot reservoir. All right, so just going through the formulas. T here, so if I'm going to the next box, which is this one kind of kitty corner from me, the middle one up at the top there, that's all about waves, or I should say periodic movement, waves, sound, or harmonic motion, waves, and sound. For that one, capital T is period, measured in time. 2 is 2, pi is pi. In this case, the capital L is the square root of capital L is length all over acceleration due to gravity. One underneath it is period of a spring. The M is mass, the K is spring constant. I don't know why my mouse isn't showing up. The third one down, period is equal to 1 over frequency. They're inverses of each other. Velocity of a wave is equal to frequency times wavelength. Intensity is equal to power of a wave divided by 4 pi r squared, or the area kind of moves out. Fn open, that'd be fundamental frequencies, and you'd have different fundamentals like first, second, third, is equal to n, whatever fundamental you're looking for. V is the speed of the wave, or the speed of sound, divided by 2L, the length of the tube or the length of the string. The fundamental frequency for a closed system is n, the fundamental. V is still wave speed over 4L, 4 times the length of the tube or string. All right, so going way over, if I do this correctly. So now if I move myself over this way, now it's this one up here, kitty corner from me. I know, movie magic. That's all about light. So that would be like the index of refraction stuff, and then like the mirror lens ray tracing, the formulas for that. N1 is the index of refraction for material 1. Sine theta 1 is what's the angle in that first material that is going to hit the boundary between the mediums at. N2 is the index of refraction for the second medium. And then sine theta 2 is just what's the angle, the refracted angle. So 1 is incident angle, 2 is refracted angle. N is equal to sine theta 1 over theta 2, or theta I over sine theta r. It's also equal to the speed of light in a vacuum divided by the speed of light in the medium. 1 over f, in this case f is the focal length, is equal to 1 over the object distance plus 1 over the image distance. So DO is object distance, DI is image distance. Capital M is magnification. HI is image height. HO is object height. And I did include that next table there just to help you know. So for F, it's positive in concave mirrors and convex lenses. You have to make your F negative for convex mirrors and concave lenses. To know you did it right, if you get a real image, your image distance will be positive. If you get a virtual image, your image distance will be negative. If you get an upright image, your magnification will be positive. If it's an inverted image, your magnification will be negative. All right. So that's typically all of the third quarter stuff. So going into fourth quarter, the stuff we just got done with. Up at the top, the very top is that top half that I have sectioned off. That's your electricity stuff. The bottom half is the magnetism stuff. F elect is electric force. Kc is Coulomb's constant, which I do give you the numbers for Coulomb's constant there. Q1 is just the charge of whatever the first thing is. Q2 is the charge of the second thing over r squared. What's the distance between them squared? So Coulomb's constant is 8.99 times 10 to the ninth. The Newton meter squared per Coulomb squared, that's just its unit. It doesn't affect the math at all. E is electric field strength is equal to Coulomb's constant. Q is the charge over r squared, the distance from that charge squared. We have another equation for electric force. It's just charge times the electric field strength. Then we can start looking at changes in electrical potential energy. It's just negative charge, electric field strength, and then the distance the charge moves in. Going down to the second row, no idea if that's going to show up or not. We talk about difference in potential difference. Delta V, measured in volts, is equal to negative electric field strength times distance. We can go back to still look at changes in electrical potential energy. It's just charge times that potential difference, that change in potential. Capital C is capacitance. It's just equal to the charge divided by the voltage. Potential energy, again, 1/2 charge times voltage. We have current, I is current, is equal to voltage divided by resistance. We have electric power, which is equal to either current times voltage, voltage squared divided by resistance, or current squared times resistance. To find the resistance for resistors in series, you just add them up. To find resistance for series and for resistors in parallel, you're going to add up the reciprocals of all of them. Whatever that is, raise it to the -1 power. All right, the bottom half is the magnetism stuff. Magnetic field strength, B, is equal to the permittivity of free space. That's a funny looking U thing. Times current divided by 2 pi r. And then r is just how far away you are. The permittivity of free space is a constant, kind of like Coulomb's constant, except this one's equal to 4 pi times 10 to the -7th Tesla's meter per amp. Okay. Once again, the Tesla meters per amp doesn't affect any of the math. It's just the unit for the constant. Magnetic field strength is also equal to the permittivity of free space times the number of loops in a solenoid divided by how long the solenoid is times the current going through it. The magnetic force is equal to the absolute value of the charge, so positive or negative doesn't matter, it's going to end up positive, times how fast is the charge going, times the magnetic field strength, times the sine of theta. So if it's going perfectly perpendicular to the magnetic field, that's the sine of 90, which is 1. That's the maximum magnetic force you can get. That's for a moving charge. Magnetic force on a current carrying wire is equal to current times the length of the wire times the magnetic field strength, and again, times that sine theta. And this part was just for honors. Since the force on a moving charge does cause circular motion, we can tie together the centripetal force and the magnetic force equations into mass times velocity over the radius of kind of that curved path is equal to absolute value of the charge times the magnetic field strength. All right, so once again, I didn't go into details into how any of those worked, what any of those tell us. I just wanted you to have all of the equations you need to take the final. Okay, and then I'll get a link to the playlist that go into detail for each of these things. All right, good luck.